Okay, hi everyone. So this is just picking up from class when I talked about um, equations in exponential form. That's what these are, okay? And their equivalent counterpart in what it's called logarithmic form, all right? And from what I understand, you did do logarithms last year in Math 2. Maybe not extensively, so I am just going to renew them, refresh you right now, okay? Um, one of the things that I want you to pay attention to is when you look at an expression in exponential form, that which is solved for, which means that which is isolated, is the result of the exponentiation. Okay, this is called an exponentiation, something raised to an exponent. What is solved for when you have an expression written in logarithmic form is the exponent. Okay, so a lot of times when you read this as log base 3 of 9 or log base 4 of 2 or log base 7 of 1, the narrative you should be telling yourself in your head is the exponent that the base 3 is raised to yield 9 equals 2. Okay, the word logarithm actually has its root in exponent of. Okay, so the exponent that 3 is raised to get 9 is 2. The exponent that 4 is raised to yield 2 is a half. All right, so again, but the point here I want to raise is that in logarithmic form, the kind of spotlight is on the exponent of the base here, okay? In exponential form, the spotlight is on the result of the exponentiation, okay? So what we have to just become fluid with, and that's your handout that I gave you in class today, is looking at things like this and becoming fairly comfortable with evaluating logarithms. Um, especially when they become a little bit more involved. Um, okay, so why don't you go ahead right now? Some of you probably can do this very quickly. Just evaluate these logarithmic, I can't say equations, evaluate these logarithmic expressions, please. And then you can either replay me or do them right now. This is 3, this is 1, this is -3, and this is 2, okay? I want to talk about this right here. Logs with a base of
Hello,
10 are
everybody.
called... Okay, excuse me, Justin, hang on, honey.
This is Paulus back in here.
Okay, Justin,
Did you see their YouTube channel?
Okay, I'm trying to do some work, okay?
Okay.
Okay. Logs of base 10, these are called common logs. Okay, common logs are logs of base 10. All right. And the reason why, you're probably wondering, why are base 10 logs so common? And it has to do a little bit with scientific notation. It has to do with converting a logarithmic relationship to a linear one. The base of 10 turns out to be very, very convenient. Okay, we'll get to logarithms in much more detail, including logarithmic functions, properties of logarithmic functions, solving logarithmic equations. Right now, for this screencast, we're just getting reacquainted with evaluating log expressions, okay? But common logs are logs of base 10, and when you have a common log, you will often have the base omitted. So when there is no subscript here of a 10, that means, and the assumption is it's a base 10, you can say log 100 equals 2. When you say log 100, the implication here is that the base is 10, okay? There's another logarithm called a natural logarithm that has to do with a number, that's the next best friend of ours in the irrational number realm, which is called the number e, okay? And we will talk about natural logs in due time, okay? Okay, so this screencast is actually very short. So what I want you to do at this point is just finish that handout that I gave you in class, which is just a quick blitz through evaluating logarithmic expressions. I believe that's the first half. And the second part of it, or the bottom third of it, is just converting an exponential equation into a logarithmic one. And you'll also see there's answers in the back. I also then want you to do this, okay? So you're going to listen to the screencast. You're now going to go ahead and just work through that handout. But then I also want to remind you of the work we did with functions that looked like this, okay? Or functions that maybe resembled something like this. Okay, and right away, when you look at these functions, you know, we have a pretty nicely developed families of functions in our head right now. You know, we know what a polynomial function looks like algebraically, which means when we're presented with it. We know what a rational function looks like algebraically. And again, when you are presented with something algebraically, it means you're presented with, you know, the function in this form, okay, as an algebraic equation. And you'll notice here that in these equations, these are certainly not polynomial and they are not rational, because neither of those types of functions allow for the independent variable x being in the exponent. So this is something we're revisiting, that we revisited, I believe, late September, early October. These functions here are called exponential functions. And the features of exponential functions are precisely what I just said. The independent variable x is in the exponent. The base, okay, the base of the exponent is a constant. You know, what's so funny is later on in calculus, probably a year from now, it's really interesting how people will confuse and forget what's what, right? This is a polynomial function. The variable x is the base. The power is integral. This is an exponential function. The base is a constant. X, the variable, is the exponent. So these are exponential functions, all of these, okay? And now you know what an exponential function manifests, what it looks like algebraically. What I'd like you to do below for each of these right here is go ahead and sketch each of these functions, okay? And after you sketch these functions, I want you to make any kind of conclusions you can about horizontal asymptotes of these three functions. And I want you to remember that horizontal asymptotes describe end behavior. Okay, and end behavior can be described using a particular limit as x approaches what? Yes, positive and negative infinity. So what I'd like you to do now is cycle back to exponential functions, sketch these with reasonable accuracy, include any asymptotic behavior, describe those asymptotes using a limit statement. And also, while we're here, why don't we talk about the domain and range of these three functions, okay? And that will set us up nicely here for Monday. There is no Algebra 2 text homework, so my apologies if you had to lug that home. But you know what, boys and girls, you can thank me for, giving you something that will make your muscles be nice and hearty, which Arusha in particular will thank me for. And if she wants to tell you why, I will leave that up to her. Good night and have a wonderful weekend.
Good night.